Okay, so what we got, so I need to remember where we got to. I had to stop because I had to delete data off the phone. So he had this idea, most of the atom is empty space. So the next thing that Rutherford had to try and explain from his experiments, and he did over 100, this experiment was done over 100,000 times. That comes up in exam questions quite a lot because, why was it seen as valid by other scientists? Well, it's valid because there was so much data taken. So the ones that were deflected, now note, the alpha particles do not hit the nucleus. That's an important thing in exam questions, that you talk about them being deflected or reflected. Don't talk about them hitting the nucleus because they never actually hit the nucleus. They can't get close enough for that to happen. They're repelled before that occurs. So the fact that some were deflected came to the conclusion that the nucleus must be positive. It's the idea the nucleus must be positive because positives and negatives attract, but positive and positive repel. The alpha particle is positive, so if it's repelled by the nucleus, it must be positive. So the nucleus must be positive to repel the positive alpha particle. So that was the next thing that Rutherford explained. Now the thing that he thought was totally impossible when he first saw it, which is why he did it again and again because they thought they must have made a mistake, was the fact that some of them were deflected by more than 90 degrees, i.e. they came back on themselves. Now to explain this, he came to the conclusion that the nucleus must be, it's very few did this, but the nucleus must be very small and very dense. So Rutherford's simple experiment really of firing alpha particles at a gold leaf, a thin sheet of gold leaf, observing what happens to those particles. What they had was a big screen, a luminescent screen, and every time one of these alpha particles hit it, the screen lit up. So from that they could deduce, they knew how they were firing the alpha particles, and then they could see if it passed straight through, then the screen would light up straight ahead. What they were noticing, it wasn't, that some were being deflected slightly, and from that he came to the conclusion that the nucleus must be positive because positive charges repel positive charges, and they noticed that some actually were deflected backwards, and from that they came to the conclusion that for that to happen, the charge and the mass of the atom must be concentrated in a very small nucleus. The fact that most pass through led to the idea that the nucleus is mostly empty space. So from Rutherford's model, he then came up, so he had this evidence, and this evidence backed up his new model for the nucleus, which is the one we use today, which is the idea that you have the nucleus, and inside that nucleus you have the protons and you have the neutrons. Protons positive, neutrons are neutral. Both of these have a mass of 1. So both of them have a relative atomic mass of 1. So that nucleus is where all the positive charge is concentrated and where most of the mass is concentrated. And then he decided that around that, a man called Bohr came up with this really, the next bit, around this idea of shells, which we talk about today, and energy levels, is that the electrons, so the electrons, which have a charge of -1, and a mass of 1/2000th, yeah, or 0.005. So hardly any mass in the electrons, and most of it is empty space. If this was the size of say I was at the school and this was the size of an atom, sorry, this was the size of the nucleus was that size, then the nearest electron would actually be somewhere past Asda towards the train station. That's how much empty space there is in an atom. This is 10,000, the sort of diameter of this is 10,000 times smaller than the diameter of the whole atom. But most of it is empty space with these very, very small electrons orbiting around in energy levels or shells. So that's what they came to. The neutron, I mentioned another man, Chadwick. The neutron was discovered by Chadwick much later on, and that helped explain how the nucleus had so much mass. Yeah, Rutherford knew about protons and electrons, but he didn't know about neutrons. Chadwick came up with this, and then we added in neutrons to the nucleus. So what you've got to be able to do really is explain that alpha scattering experiment and how that led to today's theory that electrons are in energy shells. Most of the atom is empty space and concentrated in a very small nucleus is the positive charge from the protons and the neutrons and most of the mass. So hopefully you've been able to see this. I'm going to try and put it together tomorrow and send it to you, but hopefully this will help in the basics of the structure of the atom and how it went from Thompson's plum pudding model, and then an experiment by one of his students when he moved to Manchester Rutherford led to his model of the atom, and then how since then Chadwick, another scientist, his experiments discovered the nucleus, and then how there was a man called Bohr, his experiments showed how electrons are in these energy levels, which are the orbits, the shells that you've learned about in chemistry, and when you have to draw the electron structure and you put them into shells. In reality, the electrons, you can't actually say where an electron is. It's most likely to exist within this area. At any one point, you can't say exactly where an electron is. It could be here. It's most likely to be here in the energy shell. I suppose, first shell there's 2 electrons most likely, and then the next shell there's 8, and so on. But in reality, they could be anywhere, which is a bit weird. But anyway, so you need to know Thompson, plum pudding. He discovered the electron. He knew atoms were neutral. Because of that, he knew there must be positive charge, so he came up with this sort of blob of positive charge with these electrons in it, looking a bit like a chocolate chip muffin or a chocolate chip cookie. Yeah, they referred to it as plum pudding because that's what they ate then. They didn't eat chocolate chip muffins or chocolate chip cookies. Then came Rutherford's alpha scattering experiment, firing alpha particles through gold leaf. He saw most went straight through. Because most went straight through, he concluded that most of the atom is empty space, which we can see here. This is all empty space. Because some were deflected, remember they don't hit it, they're deflected, he came to the conclusion that the positive alpha particle must be deflected by something positive, so the nucleus had a positive charge. The fact that he saw very few, I can't remember, it's something like 1 in 1800, I need to look that up for you, but very few were deflected backwards, came to the conclusion that the nucleus is very small and it must be very concentrated charge and very concentrated mass. So very small, dense, positively charged nucleus. Hopefully this has explained some stuff. If not, I'll try again, but we'll leave it there. All right, bye.